Hello and welcome, everyone. My name is Peter Robinson, and this is Dominik Schmidt, who is from Miden, and he's going to tell us all about the Miden technology. So before you dive in and share your slides, Dominik, can you tell us a little bit about yourself?
Yeah. Hi. Hi, Peter. Hi, everyone. Happy to be here and thanks for having me. Um, at the moment, I'm the co-founder of Miden together with Bobbin and Azim. Like from my background, I I studied math and philosophy and then like did a little bit of risk management in a bank, but quite early on, I started with Ethereum actually, or like trying to scale Ethereum with the Raiden network, which was one of the first scaling solutions. It didn't really work out, but I like kept trying to scale or like think about bridging and work with Consensus and the MetaMask team. And then I met Bobbin and I went down the ZK rabbit hole because I think like, and I'm happy to present it today, did this that we can scale blockchains quite efficiently with client-side proofs. Like we get other problems, there's always a trade-off space, but I think it's pretty interesting to finally scale blockchains when we have client-side zero-knowledge proofs. And yeah, this is what I'm going to present today.
Wow, that sounds really interesting, and I'm looking forward to your talk. So please present your slides.
Yeah, sure. Second. So. Um, yeah, and since we are like a small group, so to speak, please always, when you have questions, just jump in. And I should have slides for everything now. Like, hopefully, I have slides for your questions then as well. But yeah, like basically, yeah, some slides are from our pitch deck, so they are formulated a bit more aggressively. But like, this is basically the problem that we want to solve. Like we think that with transparent blockchains, and almost all blockchains are transparent, like you cannot get mass adoption of crypto. And mass adoption of crypto would mean that everyone every day like uses crypto like cash. Like maybe they know it, or maybe it's like deeply embedded into their infrastructure that they're using that they don't know it. But like crypto should be used for like as a protocol for asset exchange, and this would be mass adoption. But like we think with transparent chains, this is not possible. And a transparent blockchain is just a blockchain that adheres to the dogma, like very high level of don't trust, verify, right? Like every blockchain, but they use verify by re-executing transactions. So they must be transparent in a way that every participant of the blockchain or every block producer needs to be able to re-execute a transaction, applies it to their own local state or to the database that they keep, to verify that Alice indeed can send Bob 5 whatever, Bitcoin, Ethereum. And this is a transparent chain. And with these chains, like you will always have limited scalability because like transaction re-execution blows up into like this execution bloat. We will always reach this problem because it blows up exponentially. And eventually we will get state bloat, meaning that you need to if you always need to be able to resync from Genesis, if you don't want to trust someone, but verify it yourself, then like the more people blockchain use a blockchain, then like it will lead to huge state bloat, and you will not be able to look it up efficiently anymore. And like another problem, and this is a real problem for us, we think it will be a real problem for everyone, is that you don't get real privacy with transparent chains. So whenever you need to have all the data handy to re-execute every transaction, it is very hard to, like everyone's activities will always be traceable easily. And like you can already see that today when you use tools like Chainalysis, it's just a bit expensive, but these tools will get cheaper and cheaper. And one day I will have on my mobile phone like a Chainalysis tool, and I get like enter Peter's Ethereum address, and it will like give me every action he always did on Ethereum, but maybe also on Solana, and like it will trace the bridges and like maybe even link it to your to Peter's real world identity. And this is already possible today. It's just expensive using Chainalysis because there's some human work involved. But like this will be possible with AI. And like in a world where everything is traceable that you ever did, I would not want to use blockchain technology. And so I would understand like that mass adoption will not be possible with transparent chains. And it is just an inherently unsafe environment. Like if like smart contracts are honeypots, basically you can exactly see who owns what and what are the biggest honeypots. The whole code is visible for everyone and the whole state of the smart contract. So bugs are actually easily exploitable in transparent chains. And so, yeah, we think we need to change that to reach mass adoption. And our solution is to move state and execution to the client side. And that is when you think of, like in the beginning, we had sequential execution. When you think of Ethereum, so users sign a transaction and the block producer like sequentially applies these transactions in a block to the state. And like it's about, I don't know, like 25 million gas or so you can put in the block. So it's a number of transactions, and they are applied sequentially. And then like an evolution of that is like what you see in Solana or Sui, or maybe even block STM from Ethereum. So you have parallel execution, right? So you would say users still sign transactions and block producers, they apply transactions in parallel if they do not depend on each other. And like then you get like quite like a significant increase in transaction throughput and latency, but like it also leads to centralized systems and like bigger failure points in the middle, whereas we suggest state and execution should stay at the edge or should be pushed to the edge. So users should keep their own state and should execute their own transaction. And the network only verifies zero knowledge proofs. And this is because like, yeah, it's hard to create a zero knowledge proof, but it's like very easy to verify it. You just check like a certain polynomial. And so it's like, in a sense, exponentially faster than re-executing a transaction. And you get like real parallel transaction execution. Yeah, just like you get some other benefits, but also some other problems. And this is what I want to talk about today. So yeah, I skipped that. Yeah, like just upfront, like we aim to, like we are on testnet and we aim to be on mainnet end of the year, or maybe, yeah, January, February next year. And then we hopefully increase and optimize certain parts of our infra to be to be able to compete with systems like Solana or Hyperliquid. This is at least the goal that we have. And yeah, maybe to show you like our thinking is basically like we have these two arcs where we try to combine scalability and privacy. And when you look at the upper arc, like the evolution from Bitcoin to Ethereum, or the next step, or why it was invented, is basically they said like Bitcoin is not programmable enough, so they came up with Ethereum, and then like the Solana people said, okay, Ethereum is just too slow. Let's make execution asynchronous. And then like another evolutionary step we see is that when you store assets in the account itself, as you do it with Sui, then you can have it even faster if it's not the problem that multiple users needs to access the same smart contract. like an ERC20 contract, for example, then but assets live, like every asset always lives in the account, then like you get asynchronicity. And then like from SUI, like we learned a lot from everything, and like we hope we push it blockchain design one step further, learning all from these other systems. And we say like, okay, let's move state and execution to the client side. And this is even faster, or like horizontally even more scalable. But also like we have assets in the account and like make execution asynchronous and so on and so forth. And on the privacy side, like after Bitcoin, there was Zcash to say like, okay, let's make things more private. And like a lot of our system is inspired from Zcash. Then we had Aleo that said, okay, let's make privacy programmable, not only asset exchange. And we try to improve Aleo like on several points. Hopefully we can make it, because it's a great system, Aleo. But we try to not invent a new programming language, and like are way more, like we hope to be way more flexible in our programming model with a more modern zero knowledge virtual machine. Yeah, and now let's dive deep into it. So, or are there questions so far? Like this is the very short version, and then I can just like give you now the long version about the architecture and everything. Okay, so yeah, as I said, like the blockchain, the core blockchain problem that we think hinders us from mass adoption is actually this verification by re-execution. So today it is like there's one block producer, and he produces, like puts a lot of transactions in a block, and then every other node in the network, so to speak, re-executes these, like looks at the block and sequentially re-executes them and applies them to their own state. And that means like all the nodes need to keep track of the entire state. Like they have different methods how to do that, like in a Ethereum Merkle tree structure, or like in a UTXO structure, like but like in at the base it's always the same. Like you need to have some sort, or you need to store this the whole state in some efficient way, and this is ever growing, and you need to like always re-execute all the transactions to be able to be sure that Alice has 5 Bitcoin to send it to Bob. And we think, yeah, as I explained before, like this doesn't really work. We actually think we need way more privacy and scalability, and that's why we try to propose another design. So actually, what we want to achieve is we don't want to re-execute all computations and put all the data on chain. And like we say, we can't scale if we have to re-execute all computations and put all the data on chain. So actually, like we have these two goals, like we don't want it, and it's also like a necessity. Privacy is like a fundamental human right to us, but it's also a practical necessity, so to speak, for scalability. And so what do we mean by privacy? So actually, yeah, there will be no mass adoption with basic privacy. And there are several approaches to privacy, but client-side CK proofs is one. We think it might be a good way to privacy, because like if you try to encrypt data or hide data on a transparent chain to achieve privacy, like it's always more expensive and slows the blockchain even more down. Like by around 10x. So like I think, or we think off-chain execution or client-side proofs is like the way to privacy that scales the best. And yeah, like without off-chain data execution, it's just way more expensive. When you like use Tornado Cash or Railgun today on Ethereum, it's just like 10x more expensive. And for scalability, what do we mean by that? Like we assume that maybe even some AI agents or so will have an Ethereum account one day, or like a blockchain account. So we think on the ballpark of 10 billion accounts. Maybe we need 100,000 TPS. Like at the moment, we don't need that actually, but like if we really want to replace cash one day or Visa one day, like that really it's like blockchain is a backbone of the financial system worldwide, then like somehow we need to reach that. And we assume there will be non-trivial transactions. So some kind of smart accounts talking to each other, or like some swaps. And this is what we want with scalability. So when we look at the sheer numbers, in terms of state, what we would need, like if we assume that one account is 400 bytes big, this is the current average, we would need 4 terabyte of state. This is manageable, like in a bigger computer in RAM probably. Like if we assume that assets would be in the account to make it more asynchronous, then you would get like to 40 terabyte of state requirements, like which is already quite a lot to make it efficient. Like an execution for 100,000 TPS, you need around 10 billion gas per second, which is like Ethereum and all layer 2s together. Like they achieve, I think, 100 million at the moment. So it's like an increase of 1000x that you would need around. Like it's not impossible, but it's also quite a stretch. And then even if you think that, yeah, also the transactions grow gas-wise, then you would need like way more. So yeah, like at least the current, like with our current technology, it would be hard to achieve this kind of mass adoption. And like another huge problem is actually bandwidth. So you need, like if you want to have 100,000 TPS, then somehow you need to send this data around. So you need, yeah, 10 megabytes per second in a network, or if you have bigger transactions, maybe 60 megabytes per second. And like I think at the moment we are at 2.5 kilobytes per second in Ethereum, if I'm not mistaken. Somewhere, no, at the moment we are at 2.5 megabytes per second. So yeah, this is achievable. Like it's a fourfold increase to yeah, to get to this like mass adoption, like scalability. Okay, so and then like in terms of yeah, computation, as you probably know, like normally computation works like on an Ethereum level, that all users sign transactions, send it to Ethereum. So this is the original model. We have the like layer 2 model where yeah, most this is not Rust, like yeah, the roll-up model basically. So where transactions are batched and proven by the L2, and then you send you verify them somehow on Ethereum itself. And by client-side proven means basically to us that transactions are executed and proven by the user on a local device, and then the layer 2 or Ethereum itself would verify these proofs. And yeah, like this would be like what we suggest, like the third one. And the same for data. Like originally all the data goes to Ethereum, leading to this state bloat. Like the roll-up model or like Validium model. So you can say most data goes to the layer 2 or to layer 1. You can compress it or do like some tricks with state diffs to make it more efficient. But if you really want to have this layer 2 security, you need to use the layer 1 as like a data availability layer. And in the Validium model, you can say, okay, the data goes to a separate DA layer, and you only put the proofs onto Ethereum. For systems like Miden, you can say like, okay, most data can stay with the user actually, and the layer 2 only tracks a commitment. So what we suggest basically, and I will show you how, is actually that every user can act as its own Validium or layer like or yeah ZK rollup. Like the user can decide, but basically the net or even the layer 2 just tracks a commitment of all my data, and I am responsible to store my own data, and this like leads to a network that is way more efficient. So yeah, what we want is basically that users execute and prove most transactions themselves. Then the network doesn't have to do it, which is more cheap and better, like it scales better. And the user store private state locally. So only the commitments go on chain. and basically like you have a chain with a lot of commitments that you can even reduce like in a Merkle tree like structure to one commitment, and then this is super efficient. And now I'm finally here to explain you how we plan to do that. So, or like how we do it, like we already tested. So basically Miden is modeled after the actor model. This is the core idea. Like we combine the actor model, which is a well-known model in computer science, together with CK, like an efficient CK VM. But how does it work? The actor model, you can think of like a database with different actors, and every actor is a little state machine responsible for its own state. And this little state machine has an inbox. So actor A can send a message to actor B. And like when actor B then gets this message in its inbox, and actor B can change its state according to this message. If like, but it's actor B is responsible for its own state. So it has like some rules when it changes its state. And if it does change its state, then it can send messages out to other actors to trigger state changes there. And this can happen completely asynchronously. So actor A can send a message to actor B and actor C, and then at the same time, B and C can change their state according to some rules. And then like the network, basically, it's like full of little state machines sending messages asynchronously to each other. This is the actor model. And the cool thing is that, yeah, messages are produced and consumed asynchronously. And we say you can build a blockchain with that. So like our actors are accounts, and you can think of Ethereum smart contracts. Actually, they look pretty similar as Ethereum smart contracts. So they can store assets. Like in this account 1, for example, you have 10 Miden tokens in the account, and it has some code interface with which you can interact with. It has like some storage where you can store data or some variables. And it has anons, like our actors are basically accounts or smart contracts. And the accounts can send messages to each other, which we call nodes. So we combine Ethereum's account model with Bitcoin's UTXO model. And Ethereum accounts are our actors, and these UTXO-like structures are nodes. And basically, you can think of like account 1. In the first transaction, we redefine what a transaction is. A transaction in Miden is the state transition of a single account. Like whenever one account changes its state, we call that a transaction. And like so, in a first transaction, account 1 creates a node or a message that now carries 3 Miden tokens. So these assets can live in these basic entities, which are actors and which are accounts and nodes. And like in nodes, there can live assets or in accounts. And so in the first transaction, account 1 creates a node carrying 3 assets, 3 Miden tokens. And in a second transaction, account 2 can consume this node and changes its state. And like whenever an account changes the state, we call it a transaction. So basically, we need 2 transactions to transfer an asset from account 1 to account 2. And this is completely independent from the state of the rest of the network. And this is how we replicate the actor model, right? So like there's a transaction whenever an account changes its state. And like you can, like as a result of your state change, there is a node or like there can be a node, and you can like in a transaction consume or produce nodes. And like this is how an account look like. As I said, like it's pretty similar to Ethereum. It has an ID, it has a nonce, some code, like some storage, and like assets. You can store many different assets. Like on Ethereum, you can only store Ether in an account, like in a native account, and like the rest of the assets are stored in these ERC20 like structures. And as I said before, like we follow the SUI model. Actually, we can think it's cool if you store all the assets in an account and there are no ERC20 kind of contracts, because then it's like way easier to parallelize things. Yeah, like this is how an account look like. And a node basically is like an ephemeral object. Like it's, yeah, you can think of Bitcoin's UTXO nodes. It's a bit more advanced in the sense that like nodes have scripts, like also executable code that cannot be changed. And like whenever you want to consume a node, you have to execute the script. So this is basically you encode into the script spend conditions of the node. And I can say whoever wants to consume this node needs to do X, Y, Z, or needs to read the Oracle data there, and I don't know, do whatever. And then when you prove that you have done all this, then you are able to consume the node and get the assets from this node. Nodes have inputs, which can be injected in the code, a serial number and assets. And basically this is, as I said, a transaction is this is inspired by Solana. When you think of a Solana program, which is a stateless program, it's the same with a transaction. Basically, it's a stateless program that injects, or as an input has the account and gets the account in a new state, right? And other inputs are up to 1,000 nodes and gets up to 1,000 nodes out. But this is a transaction, so it always only involves a single account, and this is needed to get this asynchronicity. That's why I can create a transaction or execute a transaction at the same time as Peter. And now, this is how we replicate the actor model basically in Miden. So we changed the state model of Ethereum and kind of got inspired by Bitcoin, Ethereum, and Sui. And this is what it looks like, right? So you have actors, they send messages to each other, or accounts, they send nodes to each other. And the cool thing now is that because this transaction program, the stateless transaction program, is written in a way such that our zero knowledge virtual machine understands it, I can create a proof for every transaction, meaning that for every local state change, I can run it in our zero knowledge virtual machine, which is just a virtual machine that always creates a zero knowledge proof of the correct execution of my program. And my program is a transaction kernel. So I run a transaction in Miden, I get always a zero knowledge proof out of it. So for every transaction, there's always a zero knowledge proof. And then I just send this zero knowledge proof to the network together with some new data. Sometimes I need to say, here are 5 new nodes, or but that means for every transaction and local state change, I can create a zero knowledge proof, and the network doesn't even need to know what happened in my transaction. It just needs to know, this is my old commitment, this is my new state commitment, and here's a proof that you can change that. Meaning that every account looks from the perspective of Miden, every user account or every smart contract always looks like a zero knowledge rollup looks from the perspective of Ethereum, right? So you have the old state root, the new state root, and here's a proof, the rollup operator sends a proof to Ethereum and says okay, this is a valid state change. And this is how every user on Miden basically, or every account on Miden can change its state. And so stay private. So in this transaction proof, you don't need to know what happened inside. And basically these transaction proofs, then they get sent to the nodes. At the moment, it's a centralized node, but we also want to get decentralized, obviously. And then they get the batch together. This is a step that you probably know. It's used in recursive verification. So there's a virtual zero knowledge virtual machine again, and that inside this virtual machine, you verify 5 proofs, in a batch. And then you get one zero knowledge proof out that says you correctly verified 5 proofs. And then you can basically reduce these 5 proofs to 1 proof, and you can do that several times. And in the end, you get 1 block proof. And a block describes the state transitions or transactions of every account in a certain period of time. And you can condense that to 1 zero knowledge proof. And this you can then send to Ethereum to basically make it secure, as long as you trust it. You trust the math involved that you can stack these proofs together and put it. But this is the idea. Yes, and these transaction proofs, they can be done locally. And the cool thing is in parallel, because it only involves your one account. And so you can, in theory, reach very, very high TPS. In theory, 1 million people or even more can do that in in parallel. But obviously, you reach like in this batching step, you reach the scalability in terms of a throughput bottleneck, because the question is like how fast how many proofs can you verify in one batch in this recursion step? And this is what we are optimizing. Like we think we can easily get to 10,000 EPS, so to speak. Yeah, when we use this, like there is a dedicated hardware chip for Plonky 3, which is a system that we then use to get these numbers, because yeah, there's everywhere a rabbit hole. Like the Miden VM is like a custom, like a custom built virtual machine for blockchain usage. So like it's the RAM requirements are pretty low compared to other ZK VMs, and so we can like make a lot of usage of these like FPGA chips or like VPUs from Fabric, for example, and then like to get to 10,000 TPS, like if the batch producers or batching nodes and would use this chip, then 10,000 DPS is like in the recursion step possible. But after that, we also hit some bandwidth problems. So we would need to wrap the proof again into another zero knowledge system, like a Groth16 or so, to be able to reduce it, and then you can send it around in a decentralized network. But in theory, like yeah, like this is the bottleneck. This how you can recursively batch and put them together in a block. But verification is like super fast, and you can try it later. I can send you some links of our online playground. And so yeah, in theory, this system is highly parallelizable and scales quite well. But like when you put execution and state to the user, you get other problems, obviously. Like these are the trade-offs. So like the user doesn't only need to store like his private key, which is already a problem for a lot of people, but you also need to store your state. Like no one can recover that, whereas normally the blockchain is your database, and obviously it's a latency as well. If a user executes, like creates a zero-knowledge proof in his browser, like our goal is to get it done to 1 second, but obviously yeah, at the moment in the browser, it's like with delegated proving. So like if some other server creates your proof, then you get it in 1 second, but like it would be 10 seconds in the browser. Like in Rust, it's already in 1 second. But yeah, we hope to get it done. But like, yeah, latency and state storage requirements are the problems of this system then. But like, yeah, so obviously another problem is that a public shared state, and this is what you want to achieve with blockchains. So we don't only want to do payments, but for that we also have like network transactions. So you can also basically let the network prove and execute your transaction, and that is when you have like a smart contract public shared state, like an AMM or so, that you cannot really execute locally. Or like when several people want to execute the same smart contract locally, then you have these nasty race conditions, obviously, that you cannot really solve on a protocol level. And for that, we have network accounts and network transactions. And then you can, like, yeah, protocol-wise, use a smart contract, like almost like on Ethereum. So like in our system, we try to push state and execution as much to the user as you can, but whenever so that the network, like for these minimal use case, or like for these use cases where you really need it, you can still use it like with a network transaction, basically. Yeah. So and then like accounts can be fully public, and then you can think of like on Ethereum. So the full data is on chain, and in the Block Explorer, I can look at every storage slot of this smart contract, or they can be just with this commitment, as I explained before. And then no one knows anything, and you just know the state commitment of this account. And then every account is only 40 bytes, which is quite nice. But users are free to choose whichever model they want, like a public account or a private account. Public accounts might be useful if you, I don't know, like you want to build a simple counter contract, then it's a public account. Everyone can see the state of the counter. But if you like your private wallet or your Gnosis safe, might make more sense if I keep it private. and I have like a lot of backups for my state. And so this is like, these are the two storage modes, public and private. As I said, like accounts are also like stored in a Merkle tree like structure, but like an account can be public and then you see all the assets, storage, code, and nonce. Whereas when it's private, then everything you see is just like a commitment to this account state. And so in that sense, privacy, like this is a paradigm shift, like it's a cheaper option on Miden. Whereas on Ethereum, it's the more expensive option, right? So on Ethereum, everything is public, but then you hide it and you pay for it. Whereas on Miden, you can choose like private or public, but like public means you put more data on chain, so you pay more for it. So privacy is the cheaper option on Miden. That's why like privacy for us is a means for scalability. The more people who use Miden privately, the better the chain would scale. And the same for nodes. Like nodes are, you can think of nodes are like ephemeral smart contracts, so to speak, or like short-lived objects, but they can also be like public or private. So I can have a public node and then everyone sees like what's the content of the nodes. Like I can still say only Peter can consume it, but like everyone will see it, and then it's just easy for, I don't know, if I don't really care about privacy in that sense, I can use the blockchain as a transport layer, so to speak. And private nodes like would work quite similar to Zcash, where like you would only see a commitment and no one can know, is this like from whom is this node, or is it already consumed or not, and what's inside this node. And then I have like a side channel to Peter. I always use you as an example now, would have a side channel to Peter to send him the data and he can consume this node. Yeah, the node database is just like also to achieve this parallelism is like an append-only accumulator. It's a Merkle mountain range, so to speak. So everyone, like we can just add new nodes to this accumulator, and I can never change or delete a node in that sense. I can just add stuff to this database. And the cool thing is that like I don't need to have the latest state to be able to add stuff to it, and I can still create a valid proof that it exists now in the database. And that's quite like a cool data structure, but yeah, it is. So it's a bit different than on Bitcoin with this UTXO database, but yeah, I'm happy to dive into that as well. And then there is this nullifier database to achieve privacy. So we store in the node database, you store, these are the nodes that exist, either public or private, and nothing more. And then there's the nullifier database where you say, okay, these are the nodes that were already consumed. And so we have this in two separate databases to break the linkability. So when I consume a node, that no one knows which the existing nodes now I have consumed, but I still want to prevent double spend. And this is actually quite interesting. So like every node has a unique nullifier and a unique node ID. And you can think of, I don't know, like it's just two different ways of hash to hash the data inside the node. So when you think of a node that has 3 data fields, and if you hash A, B, C, for example, like then it's the node ID, and this is what we store in the node database. And when you hash CBA, it's a different hash, and then this is the nullifier. But like these two hashes, they are not linkable if you only know the hashes. But if you have the node data, then it's quite easy to like see that this nullifier belongs to this node. So that means like an external observer who just sees these two hashes knows only that, okay, this node existed and there's another node that was consumed. And if you have the real node data, then you can consume a node and like create a valid nullifier basically, and create a valid node ID. I have a slide for this later, but it's actually quite a nice system that you can only create these nullifiers or compute them correctly if you have the whole data. So I need the whole data to consume a node, but everyone can verify that this is like a valid nullifier basically, but no one can link them together. This system is from Zcash, yeah. So yeah, we follow that here. And yeah, this is then what we have like as a global state on Miden, right? So like this is how the the block producers see the network. They have this account DB, the nodes DB, and the nullifier DB, and like this is a block. Then like the updated accounts can either be public or private. Like so, for private accounts, it would just be always a new state commitment. For public accounts, it would be the full data. You have the created nodes. For private nodes, it would just be like, these are new nodes and here's the commitment. For public nodes, it would always be like, these are the new nodes and they look like this. And then the nullifiers is just like a set of nullifiers, like inverted hashes of hashes of node data that you cannot really link to node IDs. Yeah, and this is like the cool thing is now for decentralization, like if I would have 100 different block producers, they only always need the commitments to all this data to be able to produce a new block or to verify a block, meaning that even for public accounts, like in theory, like the first validator could store all the public accounts that start with A, but the second block producer could then, for all accounts that start with A, only store the commitment, even if he knows the public data, but just to like prevent state bloat in a sense. Like it's just like someone needs to store the full data, but you could still verify a proof against only this commitment. And so like not every validator or like block producer needs to know the same data to be able to produce blocks. And so you can have like a different way of thinking of preventing state bloat. Like in theory, like if indeed 10 billion people produce Miden, that will come in handy. If we don't reach that, then it will not be that useful. But yeah, so this is basically our like storage and execution option. So you could have on-chain data, like these public accounts, public nodes, and network execution, and then it's kind of the similar system as you have on Ethereum. You can have also local execution and off-chain data, and then you would have completely private transactions and way more scalable transactions that happen. And yeah, this is like as what I said before, like if account 1 sends a node to account 2, then in a first transaction, like this is what I showed before, right? So account 1 changes its state, creates a node, and then in the first transaction, he would record a node in the nodes database. So this is just like the node ID basically is the hash of these data fields A, B, C, so to speak. And then account 2 somehow knows these data fields A, B, C, like because the user of account A sends him the node data via Signal or so, or email, or like we have a transport layer for private nodes as well. And then account 2 like would consume this node because he has the data and create a nullifier, like another hash of the node data, and send it to the network and say like, look, I correctly consumed this node. Here's the proof for it, and here's the new nullifier for you to add as a result of this transaction program. And then the Miden node or the network could say, okay, yeah, that's true. And here's a new nullifier. And then like this node is consumed. So whenever someone else tries to record the same nullifier, then obviously the nullifier is already there, but no one can link these two things together. Yeah, that's like now it was a very long monologue, and I'm happy to answer questions or jumping.
Yeah, I think there are a few questions. I know that Dev put one in and I put a few in, some of which I think you've now answered. But Dev said, where are the script? Where do the scripts reside? Is that part of a smart contract or operates in the protocol level?
Yes, like the so there are two scripts. Like best I show you in the Block Explorer itself. Then do you see my Explorer now?
Yes.
Yes. Okay. Cool. So like there are two parts of code. Like there is account code, right? So here is a public account, for example, and there I can see like this is the account code. Like it looks a bit ugly yet. Like we have a Rust compiler, but it's not yet updated. But this is like, so it lives just in the account. Like it's a data field in the account. and this is a public account, so I can look at it on chain. Like, and this is the same as when you would go on Etherscan to a smart contract and you can see the code. I can even interact with this code, like I can, as with Ethereum. And then there are nodes, and here I created nodes, for example. When I look at a public node, then you would have the same, like here is the script of the node. Like these are the encoded spend conditions, like at the moment in our assembly language again, which is like hopefully in 4 weeks we have the full compiler. So the scripts live with the account code, lives with the account. The node scripts, like I said, data field in the nodes. And then there's a transaction script, which like a user can add to this transaction program in the end to, like, for example, sign a transaction. And then you have just the transaction kernel, basically, which puts all these things together. You tell the transaction kernel, I want to consume these 5 nodes. This is their script, and I want to execute them against this account. And then the transaction kernel like puts all this Miden assembly code together, or like in the future Rust code together, and then it executes that. And so, yeah, the script lives always with the object itself. I hope this answers your question.
Yeah, it makes sense to me. So I think it's, and yes, Dev said, yes, it does.
Okay.
I had a question about, which I think I know the answer to anyway, but if the pre-state proof, so when you're posting a proof, you're going to have a pre-state, post-state, and I guess if the pre-state doesn't match the current state, then the proof gets rejected, I guess.
Yes, yes. You can think of like maybe I can show you as well. Like the zero knowledge proof has always like a public input and a private input, right? And like in the public input, there would be the old state and the new state. And this would be like, or the old state commitment and the new state commitment. And this must match what the verifier has like in his database, basically. It's the same way as like it would be rejected in a zero knowledge rollup on Ethereum. If you would say like this, either not the old state, it doesn't match, then the proof would be rejected anyway. And like, or if like the proof would result in a different state, then it would also be rejected. Like these public inputs basically are defined that you need them to send to the verifier to be able to verify it. But since it's only commitments, you don't know what's behind these commitments. But yeah, pre-state and post-state is like public output, so to speak. Or the post-state is the public output of a proof.
Yeah, that all makes sense. And another question is, so if the notes are going to be stored on the blockchain, do the unspent notes, like, do they become state bloat, essentially?
Yes and no. Like, yes. So, like if, yeah, like we at the moment it's not the problem yet, and like if it's private nodes, then it's like slowly increasing. But like we need to like we have a system of epochs that you can then also, like all unspent nodes, you put them into like a structure where, like, let's say after 1 year or so, if you haven't consumed your node, then like it's still possible, but you need to store like a Merkle inclusion proof locally, for example. So at some point they would need to discard it, or like at least someone else needs to store, like you would only store the commitment anymore if this really becomes a problem, like of state bloat, or yeah, you need a separate data availability layer. The same for nullifiers. Like it just grows much slower than on transparent blockchains, we think. But it's still like eventually you will run in a state bloat thing, or also just with the commitments probably. So you need to have a commitment for old commitments and then store this data somewhere else. But yeah, you will run into similar problems.
Yeah, it makes sense. It makes sense. And I think the other two questions I had, which was, so if everyone's going to own their own state, does that mean they have to use Google Drive or Apple iCloud or some other solution to make sure they don't lose their own data? And I think it sounds like the answer is yes.
Yes, at the moment it's like Google Cloud and your local machine. We are working with a company now for private state management solutions, and there could be decentralized solutions like IPFS or even Celestia or a Whale, and also like you need for private shared state you need a more sophisticated solution, like when we share a multi-sig together, for example. And there are some decentralized or centralized solutions where you can store that and use that. Hopefully, it will be abstracted away from the user completely, but the app producer needs to think, like the app developer needs to think about it.
Yeah, for sure. Yeah, and then you said that private notes need to be communicated off chain somehow. So so that's the answer to that question. So I think you've done all the questions, and no one's jumped in with more questions. So I think you're all good.
Perfect. Then I show your
yes,
slides, Peter.
Yeah. The merch store is still there, which is good. Buy a t-shirt. Next slide. And yes, we've got some more talks coming up. A new way of thinking about data access for blockchain. I'm going to go do a deep dive on 7702, and then Paul Bose has got a thought on Circle's currency protocol, which is a new way of thinking about sharing money. So anyway, some exciting talks coming up. And if you're here today, we're on YouTube. If you're on YouTube, join the talks live and ask the speakers some tricky questions. There's a big long Slack invite link, and as well, every now and again we have example code. So there you go. So Dominik, that was awesome. Thank you very much for giving us the latest. So you gave a talk about what, 2 years ago on Miden, and the world has changed a lot with Miden. I think your conception of the ideas has evolved so much, and it's really wonderful to see.
Yeah, it's but it's also like for a very long time in the making, I guess. At least Bob and he developed this very fast zero knowledge virtual machine for blockchain use case, already in Facebook, with their currency, and then so he started 2017 or so with it.
Yeah,
it's a very long development.
Good things take time,
Yeah.
I am sure when people were working on the wheel back quite a long time ago, they didn't, wheel 1.0, didn't just happen overnight. There was probably a few iterations.
Yeah, it's true. But if you want, you can also I want to show you this is a super easy way to interact with Miden. I just share it here in the chat. But you can try out our playground and send around some transactions, and there's no assembly coding or so needed. It's just a playground where you can use it in the browser and do some client-side transactions.
Great. And I'll share that link in the description of the YouTube video too, so people can easily get to it. So look, thank you very much again, and very good to see you. And thank you.
Thank you.
Wish you all the best. Bye, guys.
Thank you.
Bye-bye.
Bye.